This should be video Physics27EBlake, and I said something about it on the last video. All that, probably the last one. Now let's go ahead and get done with this one here and get into the chapter review stuff for chapter 6. Then we'll call that the end of it. All right, so we just did this elastic collision lab, which is actually very involved and very difficult to put together. So if it seemed easy to you, then I achieved my goal of making it seem easy. But it does not at all. Spent a lot of time on it. All right, now the gist of some of what I was talking about, let me mention this again. If you go to do an elastic collision, momentum is conserved. Well, you're going to know the masses, and you may know the starting velocities. But what if you don't have either final velocity? You'd have two unknowns in your conservation of momentum equation. And then if you try to do conservation of kinetic energy, you'd end up with the same two unknowns. Well, as long as the first or the second object's initial velocity was 0, then you can have two equations with two unknowns. And that's what I went through all that rigmarole in that one video for. And you come up with these two. It's a special case of you have a perfectly elastic collision. You know both masses. You know the one starting velocity, and the other starting velocity is a known 0. These will predict your two velocities of your objects after the collision. Not going to do it this year, but last year I apparently did some coefficient of restitution lab off that data or something. I'm not sure what I did. I'm skipping that this year. Okay, continuing with the practice 6G problems. And I think what I did was went into the first one there in the last video. And then it was just an odd ending place. So let's go on to the next one, number 2. Oh, come on. All right. So on this one, we've got momentum conserved. Page 229. And it's elastic collision, so kinetic energy will also be conserved. So you have a canoe and a raft. The canoe is heavier, moving at 12 meters per second, let's say negative. The raft is 4 kilograms, moving at 6 millimeters per second, so it's less massive and slower. When the canoe hits it, the canoe's going to keep going because it's bigger and it's faster. The raft goes to the left at negative 22.7 meters per second. That leaves you one variable to find out. And the raft, or the canoe's velocity, if you take this number, crunch this number, add this over to the other side, comes out to be negative 4.8 meters per second. Now, I want to point out something in here. If you have a I don't have it in a slick place in the notes here, but I pointed out when I went through the derivation of those equations on the next page. And Diana Cower, physics girl, in her video pointed out that that difference in velocity between the two is retained. Let me show you. If we go to our video again, on the elastic collision, okay, if you look at the rate of change of velocity here, it's about the same as there. They come together about the same speed, they go apart. Another way of saying it, which I think maybe she did in her video, is if the center of mass retains its velocity. So you had a big object hitting a smaller one, poof. The center of mass would retain its velocity, and the change in velocity between the two would be the same. So the rate that they come together and the rate that they separate is the same. Which, if I want to throw that in here, if you have a change of velocity between the two of 18 meters per second, then the change in velocity over here should be 18 meters per second. So if you take 22.7 meters per second and subtract 18, you should get 4.8. Or 22.7 minus a negative 4.8 should give you about an 18. It doesn't here because of rounding error, but it's the same thing. So I wanted to throw that in here. That's important. It's also a way to check to see if you're getting good data. It's one of the things that took so long with an elastic collision to make sure I'm getting the delta V's that are the same on both sides. All right, so when you check for kinetic energy on this, because it's an elastic collision, that should also be conserved. So if you take the raft's kinetic energy, the canoe's kinetic energy, 1/2 mv squared for each one, and add them, you get 1224. After the collision, if you take 1/2 mv squared with the new velocity for the raft, and 1/2 mv squared with the new velocity for the canoe, and add them, you should get about the same number, about 1200 joules apiece. Okay, number 3. You got a bowling ball moving to the right, it's another bowling ball at rest. Same mass. So you can do this if you want, because the ones at rest, the masses are the same. In fact, if the masses are the same and you subtract the two masses, you get 0 up here, and your other mass stops. The other one will take off with double the first mass divided by double, so it's the same speed. Notice what happens here if one mass gets really big and one mass gets small. If one mass gets really big, the first one, the second object is going to take off with double the velocity. That's why when I drop the ball, you know, the smaller one takes off. So if you have a dump truck hitting a bouncy ball, the dump truck's going 55 miles an hour, hits the bouncy ball sitting at rest, the bouncy ball's going to go 110, almost. Whereas the truck doesn't hardly slow down at all. All right, anyway. So you have 4 kilograms going at 8 meters per second plus a nothing. Gives you nothing plus 4 kilograms times 8 meters per second. And in both cases, you have 128 joules of kinetic energy. 25 kilogram bumper car moving to the right at 5.5 meters per second. There's 2 ways to do this one. Moving to the right, you can just plug the numbers in as we have them here, which is what we've been doing. But I want to show you another way to do it. You could plug in 25 kilograms times 5.5 meters per second. Strikes 35 kilograms times 2 meters per second. After the collision, the 25 kilogram car moves at 1.4 meters per second. What's the other one move? If you do your math right, it comes out to 4.9. I have a mistake in here. I'm going to go ahead and fix it now. Okay. if you look at my change in velocity between these two, it's equal to 3.5 meters per second. On this side, my change in velocity has to be 3.5 meters per second. So if I take 1.4 and this one has to be 3.5 faster, I get 4.9. That's a quick way to the answer, and it's a quick check. I had 4.9 right there. So I meant 3.5. In an elastic collision, that difference in velocities should be the same. They want you to calculate the kinetic energies of each of those, and if you calculate the kinetic energies of each, both sides should end up being about 445. Or close to. Are they equal? Yeah, they're pretty close to equal. And it's anything that's not rounding error. But let me show you another way to do this. You can take advantage of this difference in velocity to do this a way that you may find easier. And that is to make the second one sitting still and use these two equations. Plug and chug them out. Now these equations only work when it's an elastic collision and the second one's sitting still. Well, let's say it's all a matter of how you look at it. If you're this guy riding on this mass, you're sitting at 0, not moving at 2 meters per second, and this is coming at you at 3.5. So let's work it that way. And then when we're done, add 2 meters per second back in. You may like this method better. So we'll just take 2 meters per second off of everything and call this sitting still, because if this guy was riding that, it looks like it's sitting still to him, and it has to be true for all frames of reference. Now it looks like this guy's moving at 3.5 meters per second, and this guy's moving at 0. So I take my masses, which are 25 and 35, so 25 minus 35 is -10, divided by the sum of those two is 50, so something's wrong. 25 and 35 is 60. So 10 divided by 60 is 0.167 times my original 3.5 is -0.58, because it's -10 over 60. 2m1 is 50 divided by 60 times 50 divided by 60 is 0.83 times 3.5 is 2.92 meters per second. And when you're done, add 2 to everything. 2 plus 0.58 negative is 1.42. 2 plus 2.92 is 4.92. And you're right back to the same two answers. 4.9 and 1.4. Okay, just by shifting the frame of reference to make that second one sitting still. A lot of times I'll do it this way because it's easier. I think it's easier. Okay, going on to the section review, and then I'll wrap up with this. I want 2 examples of elastic and 2 of inelastic. 2 helium atoms colliding would be pretty much perfectly elastic. A helium atom is not like an oxygen molecule that's got a length to it and it can cause the other one to spin. That gets into something called degrees of freedom, which we're not going to get to in this course. But a helium atom is just a sphere. So if you have 2 helium atoms hitting head on, they're going to give a perfectly elastic collision. 2 glass spheres are close to perfectly elastic. Glass has a very high elasticity. Now it's brittle, it can't bend very far, its resiliency is low, but it has an extremely high tendency to return without loss of energy to its original shape. So that's what elasticity is. If you catch a baseball in a catcher's mitt, that's inelastic, it's perfectly encapsulated. A meteorite hitting there, that's elastic. Number 2, two automobiles collide, they don't usually stick together. Does this mean it's elastic? No. It's going to be somewhere between inelastic and perfectly elastic. You are going to convert energy into deformation and thermal energy, so the collision cannot be perfectly elastic. Okay, so you have the next one, a fullback and a football guy here. So it's an inelastic collision, they hang on to each other. So you have the momentum of one plus the momentum of the other one, but when they're done, the two masses have the same velocity. We've seen that. So we want to calculate the velocity and then their kinetic energies, the decrease in it. So 90 times 0.5 negative plus 95 times 3 is 185 times, and then you solve for the final velocity, and it's slower than each. So 0.9 meters per second. When you calculate the kinetic energies, you have 1125 for the faster football player and 428 for the slower one. Its total is 1553. When they're combined together, they're going really slow, so this kinetic energy is only about 75. So you lost a negligible amount, really. So if you take 53 minus 75, it's 14 or 1500 joules. It's mostly rounding error. Okay, a rubber ball colliding with the sidewalk. I decided to skip that one because I didn't like the book answers and I'm too tired to think up of a good one. So, yeah, you should be aware of what's going on with that. But have two soccer balls collide. One takes off, one stops. So basically, one's at rest. They weigh the same amount. One's at rest, one's at 3.5. So one hits the other one, it stops, and the other one takes off. You know, 0.4 times 0 is on both sides. Those fall out because it's 0. Divide by 0.4, you end up with 3.5 again. So the answer to the problem is the one ball sitting still is 0 joule, and the other ball sitting still is 0 joules. If you look at the ones that are moving, they're both 2.45 joules, but I think this is the answer to the problem. Okay, the rest of it's chapter 6 summary. If we get this far this week, we'll be working out of the review.